students, welcome to Sunil's tutorial. I'm Sunil Milwani and today we will be doing this chapter called as magnetism. Let's see this. Let's derive an expression for magnetic induction. Magnetic induction due to a bar magnet at a point along the axis. Right? Let's see this. Let's assume that I have a magnet. Right? This is the north pole of the magnet, south pole of the magnet, center. Right? Let's assume this length between center and north pole is L. Center and south pole is also L. Okay. Now let's try to find a point along the axis. Let's assume that there is a point P along the axis, which is at a distance of D from the center of the magnet. The distance between the center of the magnet and the given point P is D. Now, the north pole is going to exert some force on this point P. Let us assume that the north pole exerts a force, say magnetic induction of B1. The south pole will also exert some force at point P, some magnetic induction. If the north pole is going to exert a force in outward direction, obviously the south pole will exert a force in reverse direction. So let's assume that this is the magnetic induction due to south pole, right? Let's write the assumptions down. Let us assume let P be a point on the axis of a bar magnet at a distance D from the center. Let us assume let M be the pole strength. Right? 2L be the magnetic length. And let's assume M is the magnetic dipole moment. Right? In which case I can therefore say that magnetic dipole moment is pole strength into the magnetic length. M is equal to M into 2L. Now let us assume let B1 be the magnetic induction at point P. Be the magnetic induction at point P due to north pole. Right? Then I can therefore say that B1 is mu 0 upon 4 pi M upon NP square, where mu 0 upon 4 pi is the permittivity of free space, M is the pole strength, and it is directly proportional to the pole strength and inversely proportional to the square of the distance. Right? Now, this induction is going to be directed away from the magnet. B1, as you can see in the diagram, is directed away from the magnet. This induction is directed away from the magnet. This induction is directed away from the magnet, right? The magnetic induction B2 at point P, the magnetic induction B2 at point P due to south pole is given by B2 is mu 0 upon 4 pi m upon sp square. Right? Now this induction is going to be directed inwards. I can say that this induction is directed inwards towards the magnet. Right? Therefore, the resultant magnetic induction at point P, resultant magnetic induction at point P will be B, which will be nothing but B1 minus B2, right? Now B1 we found out as mu 0 upon 4 pi. I can take common. This will be m upon np square minus m upon sp square, right? This is mu 0 upon 4 pi m, right? Now guys, if you look at the diagram, np is going to be nothing but d minus l, d minus l the whole square, and sp is going to be nothing but d plus l the whole square, right? So in that case, this is going to be nothing but mu 0 upon 4 pi. This can be written as, if you solve this, this will be nothing but, in the denominator this is a minus b, a plus b. So a square minus b square the whole square, and in the numerator you will get 4m dl. That's, you're going to take this here, so that will be d square. LCM if I take, d plus l the whole square will come here, d minus l the whole square, and then when you expand, this is what you will get, right? Now this can be written as mu 0 upon 4 pi, 4m can be written as 2 into 2 ml into d upon d square minus l square the whole square. But 2 ml is nothing but magnetic dipole moment, so this will be nothing but mu 0 upon 4 pi 2 md upon d square minus l square the whole square, right? Now for a distant point from a short bar magnet, for a distant point from a short bar magnet, for a distant point from a short bar magnet, I can say that L is very small as compared to D. Hence, I can say that L d square minus L square is approximately equal to D square, right? Since L is, the length of the magnet is very small as compared to the point P, the distance of point P, therefore d square minus L square is approximately equal to D square. Now if I substitute this, I will get, therefore B is equal to mu 0 upon 4 pi 2 md upon d square minus L square, I will write as d square the whole square. So this is mu 0 upon 4 pi 2 md upon d raised to 4. This and this gets cancelled. So mu 0 upon 4 pi 2m upon dq. Fine, do we get this thing clear? So do we understand the magnetic induction due to a bar magnet at a point along the axis? Next, let's try to find out another derivation. Let's try to find out the magnetic induction due to a bar magnet at a point along the equator. Right. Let's consider a small bar magnet. This is South Pole, This is north pole, this is the center O, right? Let's assume that this is the point along the equator. I want to find the magnetic induction at point P. Now, the north pole is going to exert some force at this. So there is going to be some magnetic induction due to the north pole. Right? Similarly, there is going to be some magnetic induction due to the south pole. Let's assume that north pole exerts a force of say PQ. South pole, let's assume, exerts a force of PT. Right? Let us assume L is the distance between the center and the north and the south pole. And let's assume that this angle that it makes here, this distance is L, this distance is L, this angle let's assume is theta, right? And D is the distance of the given point from the center. Okay, so let's write all this down before we go ahead. Now, one more thing. The north pole is going to exert a force in direction of PQ and south pole in the direction of PT. We have to find out the net direction in which it is going to move. We'll see that later. First, let's write this assumptions down. Consider a point P. Consider a point P on the equator of a bar magnet. On the equator of a bar magnet at a distance D. At a distance D from the center O. Right? Center O of the magnet. Let us assume that M be the pole strength, will be the magnetic length, right, and M capital N be the magnetic dipole moment. Therefore, I can say that magnetic dipole moment is pole strength into magnetic length. Now, let B1 and B2 be the magnetic induction at point P. Let B1 and B2 be magnetic induction at point P due to north and south pole. Fine, do we get this in here? Now, in that case, I could therefore say that B1 is mu 0 upon 4 pi M upon NP square. The distance is NP square, right? Now let's assume that this induction is directed away from the north pole. This induction B1 is directed away from north pole. Fine. Now let's also assume, guys, let magnetic induction B2 at point P due to south pole, magnetic induction B2 is going to be mu 0 upon 4 pi M upon SP square, right? Now I can say that this is directed towards the south pole, where I can say B2 is directed towards south pole. Fine, do we get this in here? Now, I can say that, but NP is equal to SP because the point is on the equator. Therefore, I can say that B1 will be equal to B2. Right? Therefore, I can say that PQ Therefore I can say that PQ will be equal to PT. If B1 is equal to B2, then the magnetic induction due to the two poles is going to be equal. Now if I complete parallelogram PQ, say RT, so this was my point P, this was PQ, that was directed outwards, PT was directed here. Let's complete this parallelogram PQRT, right? So in that case I can say that the diagonal PR of the parallelogram, represents the resultant magnetic induction, represents the resultant magnetic induction, represents the resultant magnetic induction due to the magnet at point P, magnetic induction at point P. Now I can say that if you look at this figure, I can say that triangle PQR and triangle PQR and triangle NPS are similar. Guys, can we just see this figure? Can we just see this figure? This was my R. I can say triangle PQR and triangle NPS. This triangle and this whole triangle down there are similar. I'm going to draw this figure here for you all again, guys. You have R, P, Q, and then you have NPS. Right? N and S. Right? So I can say triangle PQR and NPS are similar. Right? If they are similar, in that case, why are they similar? You have both these lines are parallel. You have angles are going to be convergent. Right? So therefore the two triangles are going to be similar. Therefore I can say that PR upon PQ is equal to NS upon NP. PR upon PQ is going to be NS upon NP. Therefore I can, this is by ratio property. Therefore I can say PR is equal to PQ into NS upon NP. Right? But what is PR? PR is the net magnetic induction B, right? What is PQ? PQ is B1, right? Now, B1, and we know that what is NS? NS is 2L, and what do we need? NP. Okay, we just see that NP. Now, I can say that we have this distance is D and this distance is L. So, in triangle OPN by Pythagoras theorem, if I apply Pythagoras theorem, then I can say that NP square is L square plus D square. Right? Therefore, I could say that NP is square root of L square plus D square. Now, substitute. B, instead of PR, I am writing B is equal to B1 into 2L upon square root of L square plus D square. Right? Now, I can now say that B1, but B1 we had already found out is nothing but mu 0 upon 4 pi m upon np square into 2L upon square root of L square plus D square. This is mu 0 upon 4 pi. M into 2L is magnetic induction, magnetic dipole moment. NP square can be written as L square plus D square into square root of L square plus D square. Laws of indices, mu 0 upon 4 pi M, this is L square plus D square raised to 1 plus 1 by 2. Here the indice is 1 and for square root the indice is going to be 1 by 2. So this is going to be mu 0 upon 4 pi M upon L square plus D square raised to 3 by 2. Fine. But we know that L is very small as compared to D. Therefore, I can say that L square plus D square is approximately equal to D square. Therefore, magnetic induction B will be mu 0 upon 4 pi M upon D square raised to 3 by 2. So this is going to be mu 0 upon 4 pi M upon D cube, because square and square will get cancelled. So you will get this magnetic induction. So that is going to be the magnetic induction due to a bar magnet at a point along the equator. Fine, do we get this thing clear? Let's do the numericals please. Anyone please write the numericals down? Write the numericals down. A bar magnet has magnetic moment of 30 ampere meter square. A bar magnet has magnetic moment of 30 ampere meter square. Its geometric length is 18 centimeters. Find pole strength. Find pole strength. Sorry. Now geometric length is given to you. First of all, I need to know its magnetic length. Magnetic length is given by the formula 5 by 6 into geometric length. Right? So my magnetic length will be 5 by 6 into 18 into 10 raised to minus 2. So my magnetic length will be 15 into 10 raised to minus 2 meters. But what is magnetic length? Magnetic length is represented as 2L. Magnetic length is represented as 2L. So 2L is 15 into 10 raised to minus 2 meters. Now magnetic dipole moment is given by the formula pole strength into magnetic length. Therefore pole strength will be M upon 2L. I know the value of M, I know the value of 2L. I can substitute and get the answer. The answer for this sum should come to 200 ampere meter. Next, take a mix-up please. A flat circular coil has a radius. A flat circular coil has a radius of 10 centimeters. A flat circular coil has a radius of 10 centimeters and has 80 turns. And carries a current of 0.7 amps. Find the magnetic dipole moment. Find the magnetic dipole moment. Find the magnetic dipole moment. Magnetic dipole moment is given by the formula NIA, number of turns into current into cross section area. So Ni. Now since this is in the form of a circle, its area will be pi r square. I know N, I know I know R. All I need to do is substitute and get the answer. The answer for this sum should come to 0.1758 ampere meter square. Next, take on next one please. A bar magnet has a pole strength. A bar magnet has a pole strength of 250 ampere meters. A bar magnet has a pole strength of 250 ampere meter and magnetic length of 8 centimeters and magnetic length of 8 centimeters is placed in a magnetic field of 6.8 into 10 raised to minus 5 Webers per meter square at an angle of 60 degree. Determine the magnitude of couple. Determine the magnitude of couple. Determine the magnitude of couple. Now first thing I need to know is the magnetic dipole moment. Magnetic dipole moment is given by the formula pole strength into 2L. I know pole strength, I know 2L. So first I've used this formula. Then they've asked me to find out couple. Couple is nothing but torque. Torque is given by the formula mb sin theta. M I have calculated, B and theta are given to me. All I need to do is substitute and get the answer. The answer for this sum should be 3.926 into 10 raised to minus 4 Newton meter. Next, take on next one please. A magnetic needle rotates through an angle. A magnetic needle rotates through an angle of 35 degrees when a horizontal eastward magnetic field is applied. When a horizontal eastward magnetic field is applied. If the horizontal component of the Earth's magnetic field is 3.6 into 10 raised to minus 5 Webers per meter square, find the magnetic induction applied. Find the magnetic induction applied. Right, I can straight away use tangent law here, guys. I can say by tangent law B is equal to BH tan theta, because the horizontal component and the Earth's magnetic field are going to be at right angles to each other. That is the reason why I am applying tangent law. BH is given to you, theta is given to you. You can solve the sum and get the answer. The answer for this sum should be 2.52 into 10 raised to minus 5 Webers per meter square. Right? Okay, we'll stop this here for the day. Thank you very much.